K1, rotational kinematics. I remember being fascinated by the analogy, how you could write down all the equations by analogy from translation, and that's what we're going to do right now. Physical quantity, symbol, definition, and units. And we're going to make a list. We're going to make a corresponding list over here. Quantity, symbol, definition, and units. So we start out here with position, and that's going to be x in kinematics. We have already studied that in somewhat detail. And this is a measure of a distance from a reference. So we're measuring here distance, and the units for a distance, meters, for example. Now here the quantity is going to be an angle, symbol theta, and the definition, we're going to measure an angle from a reference. In our previous section, we took that reference here to be 0 degrees right here, due east of the center of the circle. And the units, radians, rad. So position, and then we have velocity, v, and that would be the derivative, dx dt, or we can write that as the limit as delta t goes to 0 of delta x over delta t. Units are meters per second. Here we'll have angular velocity. Symbol is omega, and we have the derivative of the angle with respect to time, or we could take the limit as delta t goes to 0 of delta theta delta t, and the units would be radians per second, rads per second. Then we have acceleration, and that's a, and here acceleration is dv dt, or the limit as delta t goes to 0 delta v over delta t, and the units there are meters per second squared, or meters per second per second. Here we have angular acceleration. We use the Greek letter alpha, and that's the derivative of the angular velocity with respect to time, or take the limit as delta t goes to 0 of delta omega over delta t, and that's radians per second squared. So that's a cool table that we made, and in our text here, that's at www.drphys.com, we have here in the notes, a similar table. Now, the physical quantities are related. Angular velocity and angular acceleration are related, just like the angle is related to a distance, measure, position, x. So here we have already seen this connection where this is arc length, s, there's an angle theta, and this shows the connection. S is a distance traveled, like the x, and then here the angle swept out, angle theta. So we will write down this expression that we started with in this previous section. We're going to write this down as S is equal to R times theta, bringing the R to the other side. Then the limit as delta t goes to 0 of delta s with respect to time is equal to R times the limit as delta t goes to 0 of delta theta delta time. So this here is ds dt, and over here we have d theta dt, and this ds dt is the velocity along the circumference there, along the curved path. So this here is the velocity, and then this is our d theta dt is the omega. So we have this relation. V is R omega, which I like to write as omega R, since it sounds better, I think. Omega R. Then if we do the same thing again with the derivative, we keep going. We take the limit as delta t goes to 0 of delta v delta t. That's going to be equal to R times the limit as delta t goes to 0 of delta omega delta t. And this is dv dt is R d omega dt. And now we have the result that the acceleration, the linear acceleration, well, it's along the path. It's along that curve. So we would just say acceleration is equal to R times alpha, which I like to write down alpha R. So these are the two equations right here. Omega R is V and alpha R is the acceleration. Now just be careful with the centripetal acceleration. We know that if we go in a circle, that the acceleration toward the center is V squared over R. Now this is centripetal acceleration. The acceleration we're talking about here is when the revolution here is, you're speeding up. In other words, there's acceleration along the angular measure. You have acceleration. Then there'll be an acceleration for the s, which can be thought of as tangential. Tangential. So tangent. This acceleration is the tangential acceleration. With centripetal acceleration, think of a car that's driving at a constant speed in a circle. Then you're going to have V squared over R, and it's directed inward. The say door here will push someone in to the left. Now, if the speedometer should start to increase, then you're going to get the tangential acceleration. That's your A. So this is A. So you can think of it as like a tangential acceleration, and this is centripetal is a radial. It's like a radial, so that can help keep them straight. For the big analogy, we have translational kinematics, and we have rotational kinematics. First equation that we did, one of them back in the earlier chapters, V is V naught plus AT. So for the traveling in a circle, we have V becomes omega. So this is omega naught plus an A becomes alpha, alpha T. Isn't that neat? Then another equation we had was X is X naught plus V naught T plus 1/2 AT squared. So these are the kinematic equations that we looked at where we have constant acceleration. So the rotational analog here is theta naught plus omega naught T plus 1/2 alpha T squared. You might recall that when we took X minus X naught, a difference of two positions, we often call that D for distance traveled. Then we have the equation X is X naught plus, it's the average speed times T. So this would be over here, theta is theta naught plus 1/2 omega naught plus omega times T. And the last equation, sometimes I wrote as 2AD, but I'll just write X minus X naught. And that's equal to V squared minus V naught squared. So here you would have 2 times the alpha, and then theta minus theta naught is equal to omega squared minus omega naught squared. Very, very nice analogy. So it took us a whole class to derive these equations, took us a while. Here we just write them down by this nice analogy between translational kinematics and rotational kinematics.